Bismillahirrahmanirrahim. In this video we will discuss about the DC to DC converters. DC to DC converters are the power electronic circuits which have DC input at the input and provide DC output, which may be a fixed DC or a variable DC. So you can control the output DC voltage of this circuit with the help of certain control parameter. Input and output both are the DC, but they are at different voltage levels. So you can represent your DC to DC converter with the help of this block. These two lines are indicating the DC ones, and similarly this is indicating the DC. So your input is DC, your output is DC, and here you can see a control port. Control port is basically provides the signals to the power electronic switches which are there inside this converter circuit. These switches includes the BJT, MOSFET, IGBT or any other controllable switch. You have gone through the BJT, MOSFET and IGBT in your basic electronic and semiconductor devices circuits. So these switches are turned on by applying the gate voltage or the base voltage. Once you apply the base voltage or the gate voltage, that switch is turned on, and whatever is there at the input, that is available at the output if there is only the switch inside this one. But in most of the cases there will be a combination of the switches, inductor and the capacitor that will be there inside this circuit that will be processing the power. So the voltage at the input is, let's suppose V1, the current is I1. So what will be the power? Power will be the product of these two, V1 into I1. And here you have the output. So this is, let's suppose the voltage at the output is V2, the current is I2. So output power will be V2 into I2. So if we assume that this is an ideal converter, so input and the output power will be equal to each other. But as we have the switches inside this one, semiconductor switches, and there are certain power losses because of the switching, and there is a certain voltage drop inside. So what will be the result? That your output power will be less than the input power due to the losses. So you can say that this DC to DC converter is basically a DC transformer. It works like the transformer. You are familiar with the transformer. Just look at this part, that if you apply the voltage V1, you will get the voltage V2 depending upon the turn ratio. Let's suppose that there are N1 number of turns on this side and N2 turns are on this side. So from the basic transformer equation, we can relate that V1 by V2 is equal to N1 by N2. Right? So if you change the turn ratio, the output voltage will be changed. So same is going to happen over here, that you have certain input and you have the output. So you can say this control signal is basically the turn ratio controller. If you control this one, and then you can change the output DC, right? So what is this control signal? This control signal is basically, you can see over here, it is a signal giving you the certain duty cycle. What is it? Do you mean by the duty cycle? When you are going to turn on the switch, you are going to make the voltage high, and when you want to turn off the switch which is there inside this controller, you are going to make this voltage zero, gate voltage zero. So you are going to turn on and off the switch which is there inside this converter circuit at a certain regular frequency. So that you can see over here, this is one cycle, and then you are going to turn it on again and then off and so on. So you turn on and off your switch at a certain frequency, right? So the time for which your switch will be in the on state as compared to the total time that is said to be the duty cycle. So duty cycle is equal to T on over T, where T is the total time period corresponding to one switching cycle and T on is the on interval. So your switch is on for this much interval of time because you have applied the gate voltage or the base voltage, right? So when you are going to apply this one, your switch will be turned on, and when you are going to remove the gate voltage or base voltage for the interval that is equal to T off, so this one is the T off interval, right? So for that your switch will be in the off state, right? So this is your control signal, and you control the duty cycle, that is the ratio of the on time to the total time. And by controlling this duty cycle, you can control the output voltage of this converter. Later on we will see it in detail. So there are three types of the DC to DC converters. The first type is the step down converter. In the step down converter, your output voltage is less than the input voltage. That is the case. Output voltage is less than the input voltage. So such converters are said to be the buck converters. Then the second type of converter is the step up converter. In the step up converter, the output voltage is higher than the input voltage, and such converters are called the boost converters because they are going to boost up the voltage. And the third type of converter is the combination of the step up and step down, in which you can adjust either the voltage higher than the input or the voltage lesser than the input depending upon the control signal that you are going to apply. And the control signal is this duty cycle. So by controlling the duty cycle, you can control the output voltage. Either you can set it up or set it down with respect to your input. So such a converter is said to be a buck boost converter. So there are basic three types of the converters based upon the output voltage. One is the step down converter, that is the buck converter. Second one is the step up converter, that is the boost converter. And the third one is the step up or step down combination. So that is the buck boost converter. So you have the input port, you have the output port, and you have the control port in these converters, and you control the output voltage with the help of the duty cycle. And this you can consider it like a transformer, because in the transformer, by changing the turn ratio, you can control the output voltage. Similarly over here, you can control the output voltage by controlling this control signal. So later on we will see its detailed operation in the upcoming videos. Okay, now let's look at the basic operation of a switch that was being explained in the last slide. So let's suppose that we have a switch over here, and that is a BJT. So you can see a control port over here, the PWM control signal, which is applied. So on this side you have the constant DC voltage that is applied to this circuit. So that is shown over here, that your input voltage is constant, and at the output what you are going to get when you are going to turn on this switch by applying this gate voltage. The gate voltage is usually between 5 to 15 volt for the power electronic switches. So when you are going to apply this gate voltage or the base voltage, so when you are going to apply it, the switch will be turned on, and whatever voltage is over here, that will appear over here. So the output voltage for this interval of time will be this one, right? And if we assume that there is no voltage drop across this switch, the whole of the input voltage is going to appear across your output. So input voltage is equal to output if you assume the ideal switch, right? So basically you have amplified according to the gate signal. This was your gate signal, and when your switch is turned on, so your input voltage appears at the output at the same pattern. And if your switch goes off, if you remove this gate voltage, if you apply this one 0 voltage at the base of this one, so your output voltage will be 0, and that you can see over here. And then once again you are going to turn it on, so you are going to get output voltage, and when you are going to turn it off, you are going to get nothing at the output. So whatever is the gate signal that is varying between 0 and some high logic, and that high logic may be 5 volt, 15 volt, that is amplified, and you will be getting the same output voltage waveform, but at the higher voltage level that will be according to the supply that you are going to connect. So the constant input voltage was applied, but what you are going to get at the output, you are going to chop this area. This area is no more there at the output, so only this part is there at the output. So you have changed the area at the output by controlling the gate signal, and that's why we are going to call it the chopper circuit, because you are chopping the area. So control signal is amplified to the supply level, right? Assuming that there is no voltage drop across the switch. But in the practical switches there is the voltage drop, and let's suppose that this voltage drop is equal to plus minus VD, right? So when you will be considering the practical circuit, so for that case the voltage that will be appearing at the output will be slightly lesser than your supply voltage level, and that difference will be according to VD. That's the voltage drop across the switch, right? Okay, now let's look at this complete cycle. Let's assume that this interval is equal to T, that is defined by the frequency of the operation. So T is equal to 1 by F, right? So that is this time. So out of this, for this interval, your switch is in the on state, and let's call it that is equal to T on, and your switch will remain in the off state. So let's call it that is equal to T off. The sum of this one, T1 and T off, should be equal to T. So we can write down this equation, that T is equal to T on plus T off. So let me call it equation 1, right? So Now using the definition of the duty cycle, that duty cycle is equal to the ratio of the on time with the total time. So you can say that the T on is equal to D into T. So this interval, the on interval, can be represented as D into T. Okay, now what will be T off? Using this equation over here, you can say that T off is equal to total time minus T on, and T on is equal to dt, right, that you have defined over here. So using this one over here and taking T common, I can write it 1 minus D into T, and now onward I will call it 1 minus D is equal to D prime, right. So this interval, the off interval, this one, this is D prime into T. So T off is equal to D prime into T in terms of the duty cycle. D prime is the you can say the duty cycle of the off time when your switch is in the off state, right, and T on by T is simply the duty cycle defining the on time of your switch. So T off is equal to D prime into T. So from here I can write another equation, that is dt, that is on time, plus D prime into T, that is the off time, that should be equal to total time T, right, that should be equal to the total time T. So we can say that this D plus D prime will be equal to 1. Duty cycle cannot be more than 100% if you talk in terms of percentage, right. So over here I can say that the switch is in the on state for around about, let's suppose, 60% of the total time. So duty cycle is 60% because T on is 60% with respect to this one. So duty cycle is expressed in terms of percentage as well, and that represented for how much time your switch was in the on state. So sum of the on and the off time will be equal to 1, right. Okay, now let's move to the next slide. The DC value of a function can be calculated with the help of this expression. You integrate your function over the time period, as you can see over here, and then you divide this by 1 by T. So when you are going to integrate a function, what you are going to get? This is basically the area under the curve, this integration, right. So area under the curve is evaluated, and then you divide this area by the total time period to get the DC or the average value, right. DC value is the average value. So if you go back and look at this slide, where will be the average value? The average value of this signal will be somewhere in between, and that depends upon the area that is covered. If you are going to cover the whole of this area, as you can see, this input was there, right. So the whole area was being covered. So you have the maximum DC output. But once you are going to chop the area from this waveform, so area covered is going to be reduced, so the average DC voltage will be reduced. If you chop more area, more reduction will be there in the DC voltage. So that you can observe over here. If we have the small duty cycle, means you are going to turn on the switch for small interval of time and you are going to keep it off for a longer interval of time, then this is your average value. But if you increase the duty cycle by keeping your switch on for a longer interval of time, so you are going to cover more area, so your average DC voltage will be higher in this case as compared to this case. So duty cycle, for the higher duty cycle, you will be getting the higher DC output voltage. So output DC voltage depends upon the area under the curve of the selected cycle. So by chopping the area, the output voltage, that is the DC value, can be controlled, and that's why we call that it is the chopper circuit, because we are chopping the area. So now let's apply this formula over here. The DC value is given by 1 by T into integration of the function. So what is the function that we are going to get at the output? When our switch is turned on, if we assume that there is no voltage drop over here, so this is the voltage that we are going to get at the output. So output voltage is equal to the input voltage or the supply voltage. So we will have to integrate this supply voltage from 0 to from this point to this point, that is equal to dt. T on is equal to dt, right? So we are going to integrate it from 0 to dt, right? And this integration, if you solve it, Vn is the constant one, so taking it out, it will become Vn by T. So integrating this 1 with respect to dt, so you are going to, with respect to time and applying these limits, you are going to get dt. So this will be cancelled out and Vin into D. So what is your output DC voltage? DC voltage is equal to Vin into D. So if you keep your input voltage constant, if you change the duty cycle, you can change the output voltage, right? So we can say that this output voltage is the function of the duty cycle. And what is the duty cycle? Duty cycle is the ratio of the on time with the total time. And you are periodically applying this one and you are going to get the output voltage at your converter circuit, and that will be according to the area that will be covered by these waveforms. So whatever is your gate signal, that is basically amplified at the output, and the output DC average value is controlled by the area under the curve. Okay, so here is the definition of the duty cycle. It is defined as the ratio of the on time with the total time and is represented as D. So duty cycle is equal to T on by T, that is the on duty cycle. And if I talk about the duty cycle of the off interval, so duty cycle for off interval, that is represented as D prime, and that is equal to, you can say, T off over the total time, right? And that will be equal to 1 minus D. And we have seen that the D plus D prime is equal to 1. The total duty cycle can be equal to 100%. And what we have concluded over here, that V out is directly proportional to the duty cycle. If your duty cycle is increasing, your output voltage will be increasing, and if your duty cycle is decreasing, your output voltage will be decreasing, right? And if I quickly look at it, if we connect the inductive load with this circuit, so how this circuit is going to operate, let's suppose that this is our switch, and over here we have the control part, and we have the constant voltage that we are going to apply, that is, let's suppose V in, and at the output we are going to connect the resistance as well as the inductance. RL load is being applied. So if RL load is applied when you are going to turn on your switch, so whatever is the input voltage, that will be appearing across the load. So if I say that this is my gate signal, this red one is the gate signal, right? I am going to turn on and off the switch. So let me mark it VG, and let's mark the output voltage with the green color. So whenever I am going to turn on this switch by applying the gate voltage, VG is the gate voltage over here, so we will be getting at the output the voltage level of the input, right? And when we are going to make the switch off, output is 0. When we are going to turn it on again, output is going to appear, and when we are going to make it off, then output voltage is going to be 0. So this is our output voltage waveform, right? And this one is the gate voltage waveform. Gate voltage, that is the voltage that you are going to apply at the base of your switch, either it's BJT or MOSFET or IGBT. So you are going to get amplified version at the output. Now what about the current? In the case of, if it resistive load, the current waveform will be exactly same. So let's suppose that this is the current waveform depending upon the magnitude, right? So this is indicating the current I is equal to simply V by R if it is the what we say the resistive load only. But in the case of the inductive load, the current waveform will be slightly different, and what that will be equal to, when you are going to turn on the switch, depending upon the load inductance, the current will be gradually increasing. So let's suppose that the current is increasing and going to become like that, and inductor is going to store the energy, and the path of the current is like that, from your source to the through your source, through your load, through your switch, through your load, back to your source. This is the path of the current, and that current is like that, current is gradually increasing. And once you turn off your switch, now what will happen? The energy has been stored in this inductor, and that energy is equal to half Li square. And what was the inductor voltage polarity? The voltage across the inductor was like this. When the current is going to flow in this direction, starting from the source towards the and completing the path through the load like that. Okay, so when the energy is stored, this inductor is going to act as a load at the moment, and it is storing the energy in this interval of time, right? So over here it is storing the energy. So energy stored is this one. Once you are going to turn it off, so the inductor will resist the change in current, and now if you want to make the current immediately 0, what will happen? Your inductor voltage that is given as L di by dt. So as you are going to make this current 0 immediately, so di by dt is very high. Delta is from some maximum value to 0 value in no time. So the voltage that will be there across your inductor, that will be approaching to the infinite. and that infinite voltage will be damaging your switch, because that will appear at the terminal of your switch, and that will be appearing across the terminals of your switch, so your switch will be damaged. So in order to avoid that one, what you will have to do, you will have to connect a diode over here like this. And how this diode now will be protecting your switch, because when the inductor will resist the change in current, abrupt change in the current, so how it is going to resist, it is going to make this positive and it is going to make this negative. You are well familiar with this operation of the inductor, that it opposes the change in the current by becoming the source, and or you can say by having the opposite polarity across its terminal. So in this situation, when the switch was in the on state, your inductor was going to act as the load. But in this situation, when you are going to turn off this switch, your inductor is going to work as the source, and when it is going to work as the source, this is going to provide you the positive potential over here, and this positive potential will turn on your diode. So path of the current will be like this, through the inductor, through the diode, back towards this one. So this is the basically inductor current. Inductor current is flowing in this loop, and the energy that was stored in the inductor is now being dissipated across the resistance. So now the current is gradually decreasing, so we can sketch it like that, that it is decreasing according to the time constant of this circuit, and let's suppose that it is going to become like that, right? So this is the current waveform. Current is not zero in this interval when there is no voltage across the load. We are assuming that there is no voltage, but in practical case, whatever is the voltage of this diode, that will be there across the load, this diode, right, because it is in parallel to the load. So in practical case, there will be 0.7 volt minus 0.7 volt across the load, but if we consider this diode ideal, there will be no voltage across the load. It will be considered as zero, but there will be a current, and where that current is going to flow, you will see that this current is going to flow in this loop, and this in diode is called the freewheeling diode, and it is essential in the inductive load, right? If you do not connect this diode, and if you have the very high current in the circuit and you make it off, that may cause the damage of your switch. So for inductive loads, this diode is connected in parallel to the load. Okay, one more thing that is important to be considered over here, that this diode will be turned on in every cycle. So you operate usually your converter circuit at the high frequencies, so you must use the diode which is operable at the high frequency. So it is a high frequency diode. General purpose diodes cannot be used over here. So it's a high frequency diode with very small TRR, rate of recovery, so that you can switch it immediately and turn off immediately as well. So high frequency diode is used which has very small value of the recovery time. So that is essentially required over here, and for your lab you can use UF series UF4007 or UF4009. These are the high ultra frequency diodes, right? Or DD54, that is commonly available, easily available. You can use these diodes in the chopper circuits with the inductive load. So for the inductive load, the current waveform will be like this, and this will be in the next cycle. When you are going to turn it on, it is going to increase again, it is going to become like that, and then it is going to decrease. So your current is like that. And if your inductance is quite high, so what will be the current waveform in that particular case? So if your inductance is quite high, so current waveform will be like that. It is never going to come to zero, rather this is the minimum value and this is the maximum value. It is changing between them. So you can say that your current is continuous. So continuous current means that it is not going to come to zero in this cycle, and that is only possible that if your inductance is quite high as compared to the resistance in your circuit, you will be having the continuous current. But if you have the low inductance, so for low inductance you can draw the current waveform like that, that it will be like that, starting over here, and it is going to become zero before the end of the cycle. So this is the discontinuous current, and discontinuous current means that L by R ratio is small, your resistance is dominant. And for continuous current, your inductance is quite high. So over here we can say L by R ratio is high, and that's why you have the continuous current in your circuit. So depending upon the inductance, the current may be continuous and discontinuous, but you need to have the freewheeling diode, otherwise your chopper circuit cannot operate with the because it will, when you are going to turn off the switch, your switch will be damaged, because this high negative voltage because of the high rate of change of current will appear across the switch terminals, and if your switch cannot withstand that voltage, it will be damaged. So for proper operation, what you should have the freewheeling diode connected in parallel with the diode, right? And by turning switch on and off at a certain rate, you can control the average output voltage of this converter circuit. Let's suppose that in this diagram, that is indicated like this. This is the average voltage, right? So this is V average at the output, and it depends upon the duty cycle. By increasing the duty cycle, it will be increasing, and by decreasing the duty cycle, it will be decreasing. So if I summarize this video, we have seen in detail the operation of the DC to DC converter, basic DC to DC converter, which consists of a switch. We have discussed the basics of the converter circuit, types of the converter circuits, basic operation of a switch, and we have calculated the DC voltage. We have defined the duty cycle, and then we have seen the operation of this chopper circuit with the inductive load. And in upcoming videos, we will see more in detail that how we can analyze and design these chopper circuits. That's all from this video. Thank you very much.